Welcome to The Explainer. Today, we're diving deep into a linear algebra problem that's got a real detective story feel to it. We're going to see how one single, seemingly small variable can be the ultimate decider of what is and isn't mathematically possible.
So, let's get right into it. The central question is this: how can one little variable, tucked away inside a vector, hold so much power over an entire system? We're about to investigate a set of three vectors where one of them has this mysterious parameter a. Our whole mission is to figure out exactly how a calls all the shots.
All right, here are our three vectors, our persons of interest, if you will. Now take a look. That parameter a isn't just in one vector. It shows up in both u2 and u3. That's the key. It's the thread that ties their fates together, and our whole investigation really is about cracking the code of that relationship.
Okay, so first things first in any investigation, we need to find out when things get interesting. In our case, that means finding the exact moment these vectors stop being independent and start depending on each other. And for that, we've got the perfect tool for the job, the determinant.
You know, the core idea here is that when vectors become linearly dependent, one of them is basically redundant. It's not free to do its own thing anymore. It's locked into a very specific relationship with the others. And it's that restriction, that lack of freedom, that is the big clue we're chasing.
So, our method is pretty straightforward. It's a classic three-step process. First, we'll line up our vectors into a matrix. Then, we calculate its determinant. And finally, we look for that magic number, 0. A determinant of 0 is like a flashing red light, a signal that tells us, yep, they're dependent now.
So we line them up, we run the numbers, and after all that complex arithmetic, the whole complicated web of relationships boils down to this one beautiful, simple expression, 1 minus a squared. It's amazing, right? All that complexity simplified.
And bam, there it is, our first major breakthrough. The only way for that expression to equal 0 is if a is either positive 1 or negative 1. Think about that. Out of a whole universe of infinite possibilities for a, only these two specific values force our vectors into a dependent relationship. These are our critical values.
So we know when things get weird. The next logical question is, how do they get weird? What is the exact relationship that locks these vectors together when a hits those two critical values? It's time to dig deeper.
So we do the math and we solve the system, and what we uncover are these explicit formulas. And just look at that. The recipe that builds u3 from u1 and u2 is a little different for a equals 1 versus a equals negative 1. These coefficients, these are like the unique fingerprints of each dependency. And trust me, this evidence is going to be absolutely crucial in a minute.
Okay, let's take everything we've learned and move on to the final challenge. The plot thickens because now we're introduced to a new character, or suspect, really, a linear transformation called t. And our job is to figure out if this t can even exist, given what we now know about our vectors.
Now, this transformation makes a really bold claim. It promises that it can take all three of our vectors, u1, u2, and u3, and map every single one of them to the exact same output matrix. Our job is to play detective and see if this claim, this promise, is even remotely consistent with the vector relationships we just uncovered.
So to reach a final verdict, we need to run three separate interrogations. We've got to test our two critical dependent cases, when a is 1 and negative 1. And just to be thorough, we'll also test a simple independent case when a is 0, kind of like a control group.
All right, it is time to bring all of our evidence together. We're going to cross-examine this transformation story against the fundamental truths we know about our vectors, and we're going to deliver a final verdict for each and every case.
Let's get the easy one out of the way first. When a equals 0, the determinant is 1, so our vectors are linearly independent. That means they form a basis, which is basically a solid foundation for the entire vector space. And a fundamental theorem of linear algebra says that if you have a basis, you can always define a linear transformation that sends those vectors wherever you want. So for a equals 0, yes, t can absolutely exist. Case closed.
Now for the really juicy one, a equals 1. Remember this relationship? This is the key piece of evidence we're holding. This equation isn't optional. It's a fundamental truth about how these vectors behave when a equals 1.
So it's time for a consistency check. Let's apply the transformation t to our vector relationship. Now, t's big promise was that t of u1, t of u2, and t of u3 are all the same thing, that target matrix. So if we substitute that in, the question becomes, do those crazy-looking coefficients actually simplify down to the number 1? And would you look at that? They do. Perfectly. The math holds up.
The math checks out, the story is consistent, the underlying structure of the vectors doesn't just allow for the transformation's claim, it perfectly supports it. So, the verdict for A equals 1 is consistent. This transformation can and does exist.
Okay, time to interrogate our final suspect. A equals -1. Here's the alibi we're testing against. This is the specific, non-negotiable relationship that has to be true for our vectors in this case. We're going to run the exact same play. Apply T, substitute the target matrix, and check those coefficients. We need them to simplify to 1 for T's story to be true. But this time, they don't. Not even close. They simplify to a totally different complex number. And that is a major problem.
And here it is, the smoking gun. We have a flat-out contradiction. The transformation T is promising one thing, but the fundamental structure of the vectors proves something completely different. The stories don't line up. It's a mathematical impossibility. For A equals -1, this transformation cannot exist, period.
So let's just step back and look at the path we took. It was a clear, logical chain of deduction. We started with one little parameter, A. We used the determinant to find the critical points where everything changed. We uncovered the exact consequence of those changes, and then we used that ironclad knowledge to test a hypothesis which led us straight to the truth.
And this whole investigation leaves us with a much bigger question to think about, right? How often, not just in math, but in physics or engineering or finance, does the fate of an entire system, the line between what's possible and what's a fundamental contradiction, all come down to the value of one single hidden decisive parameter? Thanks for joining us on The Explainer.